So today I'm going to present basically an illustrated guide to microservices. And my name is Phil Lombardi, and I work for a company building a microservices development kit in Boston called datawire.io. Just a little bit of background. As mentioned, my name is Phil Lombardi, Datawire. You can find me on Twitter as the Big Lombowski. We're building a microservices development kit to enable developers to basically build resilient microservice applications. And if you want to check us out after this, this meetup or this conference speech, check us out at datawire.io. And awesome. So this is going to be a Python talk, really. It's not going to be Plone-centric. I don't really know much about Plone, but we are a first-class Python shop at Datawire. In fact, we love Python so much that we are writing a compiler in Python so that we can transpile basically our libraries for microservices down into other languages. Right now, we support Java, JavaScript, Python 2 and 3, Ruby, and we are working on Go support actively right now. And Python and microservices, they complement each other really, really well. A microservices environment is basically a dynamic topology of these running things that are delivering business logic. And Python as a dynamic language and something that you can basically easily hack on fits that kind of workflow really well. And time permitting, I'm going to do a couple demos with some Python microservices I've kind of built to kind of show off some of the stuff I talk about. But if we don't have time, we'll just go right to Q&A. So let's kind of start off with what is a microservice? Anyone here actually working with microservices or building microservices? Cool, 1, 2. Cool. Maybe after this, you'll go off and start working with microservices a little bit more. For the people who aren't doing microservices yet, I'm going to start off kind of by describing what they are. So these are common definitions of what microservices are. You get basically people who say they're small, self-contained, narrow in scope, bounded context, independent, loosely coupled. And these are all things that basically describe properties of a good microservice. But unfortunately, no one's actually given you a good definition here of what a microservice is. You can actually think of this as basically equivalent of someone basically telling you what a Lego is. Legos are small, self-contained, narrow in scope, bound in context, independent, loosely coupled. But no one in their right mind is actually going to tell you a single Lego piece is actually particularly useful for anything. No, what people do with Legos, though, is they build awesome, awesome things. They build applications or they build structures with them. So I'm going to go with a simpler microservices definition and just kind of lay it out. A microservice is a unit of business logic. And when I say a unit of business logic, I'm basically talking about it does one or two things really, really well. For example, it sends emails to clients. It will fill out a row in a database. It could do something else like generate a template for you. These are things that they do. It does it well. It does just that one thing. And what you really do with microservices is you build applications with them. You glue them together. You take these things and you have a distributed composition of them. And you wire them together to do something that's actually particularly useful for your business. So you deliver business value by building microservice applications by using microservices. And so they build these pretty awesome things like this Lego Death Star, which is impressive in size. What do you actually get when you're combining these microservices? In reality, it's a topology. And so we're all pretty familiar, I think, with topologies if we work on distributed systems at all. You have rings, meshes, stars, lines, trees, buses. And then there's the fully connected topology, which is basically everything talks to everything. And there is, one-to-many communication, many-to-many communication. There are circular dependencies in that communication. There's all things you have to think about. And so the thing I'm going to talk about primarily today is the fully connected topology and how microservices really ends up being one of these. And so what people often call these is a Death Star topology. For example, Netflix is composed of 500 microservices. And this is actually a pretty old picture. This was kicking around the internet about 5 years ago, I think. So by now, they probably got 1,000. And also keep in mind, when people are saying these microservices, they're talking about that in the abstract sense, so that's not actually the running instances of these things. That is probably 10 times that many for, in terms of servers that are actually powering these things. And so if you looked at that picture of the Death Star, you're probably wondering to yourself, that looks like a disaster waiting to happen. Good engineers kind of don't like to see yarn balls or mud balls or any kind of ball of junk floating around. But your CXO, your CTO, your CEO, they're probably looking at that going, well, yeah, that looks ugly to you, but to me, I see a way for people to build and deliver business value quickly. I see a way for us to scale our organization from 10 developers to 100 developers to 1,000 developers really quickly, and I see the ability for us to pivot really quickly. These are all things that your C-level executives want. So while you're going, not so great looking, they're going, yeah, that looks awesome. So let's talk a little bit about topologies. We've always been working in a topological world. They're not new. They're the bread and butter of all distributed systems. And we've been living, if you've been doing server-side development for any period of time, in a world where we have the classic three-tier architecture of client talks to a load balancer, talks to a web server, talks to a database server. And then there's n number of those web servers serving up traffic, and there's n number of those database servers serving up requests for queries. So they've always existed, but that's not the end-all be-all of topologies. And topologies are powerful, so we should really kind of think about them as what they can do for us. Information flows through topologies like water flows through a pipe or current on a wire. And probably the most important factor in the performance of a distributed system is making sure things continue to flow. The classic topology, as I'll get to in a little bit, has basically some really bad attributes of failure that you can avoid if you kind of move to a microservices topology. But topologies have also kind of always been the purview of the elite. You probably have worked with architects before in your company. The architect often basically defines what your system is going to look like and then says these are the neat little places where you will plug in your business logic. So he's laying down a very, very rigid framework and basically giving you small extension points. That's great until you realize your architect got it all really, really wrong because he went off into his ivory tower and designed this thing. And so what you actually wanted to do was go off and build this thing and let the architecture come from the construction of the services, not have the basically top-down view of we're going to lay down an architecture and then build the services around it. Microservices are all about bringing topologies to developers. No longer is your architect the one who's defining what your system is going to look like, your developers are defining it. And the business logic is built by those developers and then just kind of deployed out into production. And you worry about integrating these things together. So the topology is constantly changing as well. Services come, they go, services are added and changed, new functionality is brought in with new services, some services are deprecated, some services are just removed entirely. Point is, there is no static design for this thing. It just continues to evolve and grow, very much like a living system. And topologies can solve a lot of problems. You get operational scale from basically building these topologies and microservices. You can basically put developers on specific things. You can scale it out so that when you build these microservices so they're granular enough or well-defined enough, you can have it so that people who are really good at doing one thing can go work on that. Another group can go work on, say, building a database storage engine. Another group can work on the search indexing. Another group can build the way that the data is going to be viewed. So that's really good. You can hire also a different type of developer. You don't necessarily have to go find super strong senior developers, principal developers, people who have great insight into how the system works to build smaller features, because you can break your problems down into a way that you can hand it to, say, a junior developer or a kind of like in between a senior and a junior developer and go, here's the problem, it's defined like this, build an API for it, build the logic, and then we'll figure out how to integrate it. And so integration also becomes something that gets solved in these microservice architectures. It shifts the integration problem a little bit. So your integration becomes between services rather than internally in the code. You no longer have to think about how, when you're working inside of a code base, how your change at one point in, say, the database storage layer is going to affect the network layer because you decided to refactor some core shared classes. It's split out, and you don't have to worry about that. And so you also get some reliability guarantees as well. So in a classic monolithic architecture or a classic monolithic topology, when one piece of something fails, it often takes out the app server or the entire app server. In this kind of system where you're working on a small piece of functionality, if you're working on the emailing thing, the thing that generates templates, the thing that does queries, if that thing fails, the system should be built in a way, the topology should be basically set up so that it's resilient to that failure, thus giving you a higher level of reliability. And so kind of just digging down to this, when you think about how most modern SaaS businesses work, it basically looks like this. It's the ingest stage, which is going to be where data comes in. Your source of truth is going to be where database is stored. Your transformation layer is going to be something like, I need to take the stuff that was in the database and turn it into something else. And then your presentation layer is your UI, your API, whatever protocol you want to talk to. That's where that's going on. And they all have very different characteristics on the operational thing. Ingest is network heavy, source of truth is disk heavy, transformation is disk and CPU heavy, and presentation is network and CPU heavy. I'm not saying these are absolutes, but that tends to be the case. Point is, though, by splitting it out this way, you can basically optimize for those parts of the system. So it doesn't make sense to have to pick generic systems that are both favorable for network and disk, when you can basically pick, say, EC2 instance types that are highly optimized for network, but may not have great disk performance because they're not going to do anything with disk. Same thing for disk systems. Maybe they don't care about the network, and they only care about being able to write really fast. Or you need really powerful CPUs, but you don't care about network performance or disk. So you can basically scale operationally on hardware, but you can also scale in terms of people. It's great to find generalists as programmers, but generalists often are the jack of all trades, master of none. And sometimes your business really calls for finding a person who knows how to write awesome network servers, or really knows how to write optimized database queries, or really knows how to work on building an awesome transformation or processing pipeline. And that means that if you can split it out so your system is decomposed so that these people don't collide, they don't have to worry about cross-cutting concerns in a single code base. The person who's working on the network part can work on the network part, doesn't have to worry about how the storage part is going to work if he changes things, doesn't have to think about what his implications of his code changes are going to be, perhaps even on lower level things like the hardware they're using. So maybe there's changes that cause, if you're in like the Java world, it's a JVM, you could change things, the heap could start being an issue, thrashing CPU caches and stuff like that. I'm going to skip this slide. So let's talk a little bit about reliability. In your classic system, your reliability is basically you hit a load balancer and you talk to any of these monoliths. But centralized business logic is really a single point of failure. It's actually not a case where you hit that load balancer and you go to a single failing node and then you go to healthy nodes. More likely that bug is actually manifest in all of those nodes. So it's actually a full-on failure. When you decentralize, you end up basically, you have this, you might have a concept of load balancer, but actually I'll get to this shortly. You have a new routing mechanism to work through this topology that allows you so that you have these independent systems, one monolith, your microservices, your other services, they all do independent things. And if there's a failure in one of them, it doesn't actually cause your whole system to blow up. And decentralized business logic kind of goes back to the multiple teams. You can have people working on individual things. You can have smaller code bases, and you can ramp up your developers faster, which are things going back to what your CTO and your CEO are asking for, things they really want. So can topologies give you that Death Star? They help, but not quite. You actually need to build topologies quickly, and this requires a whole bunch of tooling around it. And so people often kind of look at topologies also in the microservices versus the service-oriented architecture thing. And what I'm actually going to say here is that both are topologies of services, and people often say they're fine-grained SOA, integration pattern versus application components, organizational factors. We really need a better definition. These explanations all ignore the process that yields this topology that we're working with. So what we really say is microservices are all about service-oriented development. Architecture and development are different processes. You were in a world when you were doing service-oriented architecture, you had a lot of upfront thinking. You probably spent weeks in a room with other engineers, prototyping, talking amongst yourselves about how you were going to build this system. There was a slow iteration cycle, and it might have been months or years until you actually got good customer feedback, which is not really great in a software world where things change quickly. A service-oriented development company is kind of looking at things as an experimental system. You're going to build little features that solve problems that you have. You're going to try and get them out there. You're going to do rapid iteration cycles on those little features, and you're hopefully looking at minutes, hours, and maybe only, in worst case, weeks to get feedback compared to months and years. Both of these can yield topologies of services, but that SOA strategy won't actually let you build your Death Star. You need to be agile about that. And so how do you actually build those agile topologies? Well, you need both a change in mindset and a change in tooling. Mindset. So as I mentioned, the classical mindset is architecture first. Think heavily about the problem, go off and build. And this has kind of been ingrained into our minds as we've come up through in our careers as software engineers. There was always a guy who was more senior than us, always more responsible for the system, always thinking about how the system would be constructed. And so that person started to kind of influence how these things should be designed. But the architect's job really is supposed to be to build a system that's resilient to whatever the other developers are working on. He's supposed to lay down the foundation of your system such that when you decide to build something, it doesn't actually fail in production, and still let you plug in things into the system. And basically, his job and this architecture person or this architecture team, they come into this world basically in this modern agile topology as developer infrastructure, developer happiness teams, or what a lot of people actually call now is like platform engineering, which is kind of the modern take on DevOps. So tooling. What tools do you really need to enable this experimentation and rapid iteration? I'm not actually going to give you any concrete tools here that you should go off and like download today and use, but I'm going to kind of tell you what you need. You need basically a way to make your topology resilient to software bugs. So you need to basically know how do I have a catch-all in my system so when there is a bug, it doesn't cause a catastrophic cascading failure. How do I minimize, this thing has to also minimize the impact of bugs reaching production. So if I do author a new service and I put it out there and there is a bug, it doesn't cascade all the way up to the person who's requesting your site, and it doesn't then affect, it may affect one person, but it hopefully doesn't affect 1,000 people, and worst case, it doesn't affect millions. One is better than 1,000, 1,000 is better than a million. Point is to avoid critical software failures. Then basically, going back to that, you just need the graceful degradation of those catastrophic failure. And then you also really need a robust tool for deployment pipelines that enable both service and system level testing. And so there's a bunch of stuff out there these days. People looking at like Spinnaker, stuff like that does this. There's Asgard. There's people glue things together with Terraform and Jenkins, or you use something like Kubernetes and Mesos. All these things kind of help you do this, but they actually don't give you enough information to actually enable basically good testing of these services as you put them out there so that you can roll them back in the worst case. And then finally, you need pretty good visibility as a developer into this running system. So visibility is broken down into two categories. There's operational visibility. And when I say operational visibility, I mean basically you need to look at, say, disk, memory, network, I/O. All that kind of stuff is really, really valuable to the people who are really managing the system and making sure at the end of the day, the core of it functions and runs. But as a developer, you need insight more into how these services interact. So if you decide to build out a topology of these services and there's 15 of them and you send a request in through the first one, you actually want to be able to trace through the entire system. You want to see what actually triggered throughout all your logic. And you want to be able to do that for n different series of requests. You want to try it with different different values coming in perhaps as the input. So maybe it takes JSON to the front service and you want to see how by changing that, what pathways it goes through. That's a really, really cool developer feature that you need to have to do this kind of topology work correctly and quickly. So how do you build these tools? You gotta kind of do two things. You need to move away from a world where you're using DNS and move to a world where you're using service discovery. And you can actually use DNS as service discovery. So it's not necessarily you have to just drop it, but I'll kind of explain what I mean here. You also need to move away from central load balancers to these things that we're gonna call smart endpoints. And a central load balancer, it kind of looks like this. This is the traditional topology for basically a classic service-oriented system. There's a client, it resolves an address from DNS. That address is probably a CNAME or an A record that points to a load balancer. That load balancer is then the thing that basically routes your traffic to one server behind there. And so your routing table is very static in the sense that DNS records, the value behind it doesn't change that often. Your load balancer, it probably doesn't change its IP address very often, or it doesn't change its CNAME very often. Similarly, your routing policy is global. And when I mean your routing policy is global, it's as a client, you don't actually get to choose what server you're talking to. So think of this. The load balancer is there, and you had version 1.0 on those three orange hexagons back there. And then you go and you put, you go off and you run version 1.1. And it ends up being in the same pool behind the load balancer as it deploys. It's doing canary deployment. And you have an integration bug in 1.1. For whatever reason, that server, that 1.1, starts serving up XML, but your client was expecting JSON. And so your client sends traffic into the load balancer, and it's continuing to get happy 200 responses from the load balancer, which is sending XML from the 1.1 service. And the load balancer has nothing, doesn't know any better, really. It's serving up 200. The request is going fine. The client is exploding And the client has no way to stop sending these requests. It just keeps sending them to the load balancer. So that basically means you've rolled out this thing and you're looking at 25% of your traffic in this simple, there was 3 servers, there's now 4, 25% of your traffic is now ending up failing because of this integration bug. Microservices topology management looks a little bit different. We actually kind of get rid of the load balancer and we make it so that the individual servers are sending heartbeats to discovery. Heartbeats then go to discovery and those routes are propagated to the client in real time. And then on the client no longer talks to a load balancer, it talks directly to individual server addresses in this system. So it knows where these servers are in your network and it can just talk to them, and it has a local routing table that it can change. So when, for example, that integration bug occurs again, it can blacklist the server. So we put out v1.1 and it was serving up that invalid data. It would say, well, I blew up, I hit an exception in my client code. My client code then goes and says, I don't want this node in my routing table anymore, and it just removes it. And so it goes back to only using 1.1, and it might send a notification to your operations team and go, like, you've had a developer throw out bad code here. Go poke him, figure out how to fix it. Another really important part about this smart endpoint thing is that little yellow box. So that was the load balancer in our previous system, and think of that now as like an integrated load balancer living right next to the client. And this can manifest in one of 2 ways. You can either do it as a sidecar proxy, something like a HA proxy or an Nginx instance that runs local, and then you basically talk to local host and route requests through it, and it reverses to those servers. Or you can kind of do it the way we're doing it at DataWire, which is it's built into the libraries itself that we create. And so we can basically update the routing tables dynamically as they come in from discovery, and we can do things like have routing overrides. For example, if you're a developer and you put out a brand new service, V2, and it's actually not going to be at all in the production pathway, but you still want to test a V2 in there. By having this local mechanism to route, basically you can say, I want to, for this particular request, override and go, instead of any one of these 1.0 or 1.1, I want to go to V2. And I can send traffic to V2 on demand. So let's do a little demos. I got to see how much time we have. We got about 17 minutes left. All right. Can you guys see, or is that too small up there? A little bigger? Better? All right, awesome. So this is, I'm going to pull up our UI, which just makes it kind of easy to see what's going on in the system. Wish I had more screen real estate. All right. So I redid my demo harness the other day. I probably should have fixed it so I had like auto screens. Demo 1. So the first demo I'm going to show you is going to just show the ability to deploy new services on demand. And so what I'm going to start up is very simple. It's going to basically be 2 Flask servers running in parallel, and they're going to come online. You saw down here it updated. We see the nodes. These are running localhost for this purpose of this demo. And if I If I do this.
Bigger there too?
Oh yeah, sure. Sorry about that. So we see now it's basically going to send the traffic over to the 2 Flask services, round robining. I'm going to add in a very simple, actually Node.js service. And it's going to come up in 2 seconds. And we see it started to route traffic automatically to that Node.js service that's in there. And there's really not anything special going on in these services. I'll show you the Flask one. It's pretty standard. Actually, that's terrible looking. So pretty standard little Flask app. We got basically this thing that's serving traffic on Slash. It registered down here with the service discovery system, which we are running our service discovery system in the cloud, so it's not hosted anywhere. And you basically register with the name of the service and a version. And then when it comes in, we do a little bit of stuff here, basically all this session stuff. Like, for example, every time this traffic comes in, we're updating a log that you can see here in real time. So that's pretty cool. I can shut down this. I can then shut down. Tear down the Express one, and we will notice the Express service has gone completely away. So that's really simple. That's just adding and removing stuff. Let's show how this smart endpoint stuff can actually, though, make it so that you can be resilient to bugs, which is a far, far more interesting thing. So, kill him off. And with no more services running, we're in demo 2 now. So let's do this setup. And this is a fairly comprehensive topology that we have here. It's actually composed of 11 services running in parallel. It is basically going to be a bunch of nested services with a front end that talks to 2 more services, which talks to 2 more services, and there's a circular dependency in there as well. So I'll show you the request. Actually, I can do this. Curl localhost 5000, and we see it's basically showing you the trace through right now of what is going on, which is a bunch of. You guys still see that over there? Yeah. Over there? Okay. He said it would come back eventually. So who knows? Hopefully it does. So that's showing you these traces. Let's actually add a buggy client. This service expects JSON to be coming back as the response, but I am going to show you what our buggy service looks like. Our buggy election service is going to, instead of returning JSON, is going to return a string. That's really frustrating. Oh, there we go again. It's going to return a string that says, oops, this is a bug. So it's an example of an integration bug, exactly kind of like the one I mentioned earlier. Developer builds something, returns an unexpected thing, and your client needs to respond. So let's put that up there. And so the buggy election service is now running. We've updated the count to 12. We can see the buggy one is running as v1.1 over here in this window. And then we can put a request through it. We can put a couple requests through it. And so the first one succeeds because it didn't talk to it. But we see this one failed. It failed one time, and it's only going to ever fail that one time. It will never see that again. So it talked to the buggy service once. The client that was talking to it failed, which was the front end service, which was kind of the first service in this business, basically topology of these things. And it realized it's no good, and so we will remove it. So that shows you resiliency. By the way, what's really cool about that is this tracing stuff. We have a trace here where we can see that basically came through completely on our system. So it's a causal trace. If actually, hold on. So I can't pull the causal. Has it disappeared? Disappeared. There's so much traffic coming through here at the moment. Demo stuff. Okay, I'll still explain. So this is a causal trace. So you see these 1, 2, 3, 1, 3, 2, 4, 5. This is basically a Lamport clock. So this is what allows you to trace through your system. As you go through, it increments this counter, and every service that gets the request increments the counter as well to basically tell you where in your service this message is coming from. So if the error was actually showing in here right now, and it disappeared off just my real-time trace already, you would see the error. You would see what the basically source of the error was and what the destination server was that caused that error, and you could do some really quick debugging that way. And then, so for the final demo, I'm going to show you the routing overrides thing, which is a little bit more complicated than the previous one, but it's pretty cool. I have to use not a curl for it. I'll show you how this works. So set up the same election thing again. And so all these services should come online. Boots up. Yep, all back. And so here's what our modified service is going to look like. And it's going to get rolled out. It's just going to basically, instead of sending back the data that it expects, it's going to say, you know, modified election service. And it's going to say reticulating splines. If any of you guys are SimCity fans, you probably remember that message. And it's going to register, you know, as a modified election service that I want to talk to. And notice as I do requests to it right now, same idea as before. We're not actually sending any data to that modified service. So your production is still working just the same way it was expected. But you now want to test out the new modified service. So you would form a basically specially formatted request with a header in the HTTP request that does this. Oh, wait, I forgot to bring up modified service. That'll not work. There we go. All right, so modified election service is now running. And just to be honest, it's still not there in production, as I said it wouldn't be. But now it is. And the way this is working is basically this header up here. I put this up here just to print. It gets injected as an HTTP header. It doesn't have to be as an HTTP header, but it is for the time being. It basically is saying, instead of going to one of those election services, go to my modified election service. So as a developer, I can put something basically into a staging environment or a production environment, and then only route my traffic and my particular request to that service without ever affecting anything in production. And so tear that all down. That's the end of the demos. Let's go back to the slides. So basically what I really want to leave you off with here today is two useful definitions. Microservice is basically a node in an agile service topology, and microservices are all about service-oriented development. And service-oriented development is all about being able to get things done fast. No longer are you bound by architecture and what your architects are thinking, but it's more about just getting things built, integrating quickly, having tools that allow you to integrate, and feeling like you can get these changes out there in a confident way. And so how to build a Death Star, it's a trifecta of velocity, agility, and organizational scale. The mindset is move from architecture to experimentation, and the key technologies in this tooling are service discovery and smart endpoints. And with these tools, you can get started basically in a half hour, working on these things rather than spending 6 months building and re-architecting your system. And so to learn more, you can contact me, Lombardi at DataWire.io. You can tweet me on Twitter at the Big Lombowski. I don't check that often, but our marketing guy said I should have one, so I do. The jobs we are hiring, we're looking for Python developers always, but we're also interested in Java, Scala, Kotlin developers because we actually have a JVM backend for some things, and we're also looking for Go and Kubernetes people since those two go hand in hand, and we are very interested in Kubernetes and where it could bring us. In terms of our operational side, we are hiring for DevOps and a site reliability engineer type role. And try us out. Like the MDK, this thing I showed you is open source and free, Apache 2. Our website, you can kind of get the whole spiel. The service discovery component is going to be open source very soon. The original version is open source, but there's a brand new version we're finishing up and about ready to release as open source, so you can play around with that. But otherwise, we actually host everything ourselves. And for the Plone conference, guys, thank you for hosting today, and they would love to get some feedback about this so they can improve this conference again for next year. Any questions? None? No questions? It's got to be somebody. All right. I'll stick around though after if anyone wants to talk one-on-one. If you don't want to do group questions, but you just have questions you want to ask me, I'm happy to stick around and just chat. I'll be out there for a little bit, probably drinking some coffee and eating some of the food. And yeah, come find me. Pleasure giving this talk today.